So, welcome to Advanced Computer Architecture. So this short introductory video is about introducing you to the course as a whole and helping you decide whether you really want to take this particular course, how the course will be organized, and what you might learn. We'll also talk a bit about how it's going to be examined and the coursework and so on. Oops. So this course is basically about how the latest microprocessors work. We'll talk about microprocessors, we'll talk a little bit about the whole system into which they fit, the system on chip. We'll also talk about larger scale systems, including supercomputers, data centers, and so on. We'll focus on why computer architectures are designed the way they are, and what the alternatives are, what the trade-offs are. And particularly from a computer science point of view, computer scientist, software engineering point of view, we'll be interested in how you can make software that uses the hardware in the best possible way. How you can build a compiler. That's actually basically my personal research area, is building compilers specifically to get the best possible performance on various kinds of computer architectures. And for that, you need to understand how they work. Another aspect that I'm really interested in is how you might design a computer specialized for your problem. You could imagine designing a domain-specific accelerator, or you could think about simply tuning the architecture, the configuration of a processor for a particular problem. And in fact, one of the coursework exercises will be about that. We'll also talk a little bit about what bigger computers look like, not just data centers, but also the kind of supercomputers on which things like weather forecasting are done, where you need the entire machine to be operating with very high communication performance in a lockstep parallel fashion. We'll talk about the fundamental challenges, as well as computer architecture is characterized by lots and lots of little things to know about. And it can seem like a mess. And one of the things we will look for and dig for are the underlying fundamental principles. And there's not very much theory in computer architecture, but we will be looking out for it. The course is to some extent based upon a textbook. It's based upon this textbook. It's the 6th edition of a famous textbook. In fact, as a student taking this course, you can tell your friends at other universities that you're doing Imperial's Hennessy and Patterson course. You're doing our Advanced Computer Architecture course. This book was actually quite revolutionary when it came out. The quantitative approach is a dig, really. It's a mission set out in this book to make computer architecture more than just an art form, and to drive it with experimental evaluation using suites of benchmark programs in order to find the optimum design irrespective of your artistic preferences. The book's quite expensive. There are various ways to get it. Obviously, a good one is to get it from the library. It covers much more than we will cover in the course. It's 900 something pages. It actually doesn't cover everything that we will cover in the course either. So it's really for breadth and depth around the topics that we'll cover. But in fact, because this, even though it's the 6th edition, is a little bit, it's 3 or 4 years old, you will need to dig a bit into other sources too. This book is written by quite significant figures in our field, in every sense. So John Hennessy founded the original RISC processor company called MIPS Computer Systems. He was also president of Stanford University. He's on the board of some of the biggest companies in the business. Wikipedia describes him as the godfather of Silicon Valley. David Patterson, leader of the Berkeley RISC project, so reduced instruction set processor architecture, is another word for the kind of quantitative approach that they were bringing to the topic. His name is on a number of other big research ideas. RAID is one of them you might have heard of. He was president of the ACM, advised presidents of the United States. Their achievements have been recognized with the 2017 ACM Turing Award And in particular, we're talking about the achievements in the book. Their achievements go beyond that because they communicated those ideas across the industry. But I strongly recommend that you go and look up the web coverage of their Turing Award lecture, which is basically about the golden age of computer architecture. And that's where we're going with this course. So the course is led by me. I, in turn, lead a research group in software performance optimization, optimizing software for hardware, and that's why this interface between hardware and computer architecture is so important to me personally. We will have some support from a couple of PhD students. We nominally have 4 hours of lectures a week. If it weren't for COVID and so on, we would have 4 timetabled hours a week. What we're going to do is have some pre-recorded lectures for you to watch, and we'll have 2 hours or up to 2 hours of synchronous interactive contact time. And we will, of course, need to think hard as the course progresses how to make the best possible use of these 2 ways of delivering the course. The last couple of lectures, incidentally, will be devoted to, or we'll spend some time on preparing for the exam. The exam takes place in the last week of term. The goal of this course is to teach you how to think about computer architecture. As I mentioned to you, and as you might have figured out from a 936-page course textbook, there's a lot to learn. Or rather, you can think of architecture as being a messy business full of details to learn. What we're going to try to do is focus on not just memorizing all of these things, but testing your thinking, your understanding, your ability to ask the right questions about architectural ideas. The exam itself, what I've been doing and what I will do this year is I will base the exam on a recent article about a recent processor architecture. And when I say based exam, I mean loosely. We'll often use it to peel off into parts of the curriculum not directly related to the architecture described in the article. But it gives us a concrete focus towards the end of the course, which assures that we actually achieve the objective of the course, which is that by the end you're learning about an example of the latest thing in the latest thinking in processor architecture. Have a look at the past papers if that sounds scary or intimidating. I'm not going to tell you my exam is easy, but I think my goal has been to structure the exam to test the things that I care about, that I hope you will learn from my course. In addition to the exam, we have a couple of coursework exercises. They're lab-based. There are a couple of unassessed coursework exercises to warm you up. But for the assessed exercises, the first one is about specializing a processor architecture for a particular problem. And we'll be using a processor microarchitecture simulator to optimize the design of a single processor core for a particular piece of code that I'll give you. The second thing we'll be doing is what I call the challenge exercise, which is about taking some code, finding a machine that you're interested in, and making that code go as fast as you possibly can on whatever hardware you pick. And of course, we will support you with advice and tools and so on for all of these things. So here's an attempt to give you an outline of the entire course. So chapter 1, what we're going to do is review stuff which you kind of should already know. So introductory processor architecture, simple stuff like pipelines and the elementary elements of cache architecture. We will cover those more or less from the beginning, but somewhat quickly. And the objective is really not to teach you all that stuff from scratch, but to establish, by looking at these simple ideas, some of the terminology, some of the ideas, some of the issues that we will need to be addressing later in the course. From there, I'm going to dive into caches and the memory system. If you look at similar courses around the world, and there are many similar courses around the world, you'll see that different lecturers choose different sequences of presentation of some of this material. I'm going to put the memory system early because it's so important. Often when we think about computer architecture, we think about the design of the functional units and instruction scheduling and branch prediction and all of that. All of that's important and we will study it, but often we neglect that what we need to be doing is maximizing the performance in the memory system. We need to be maximizing the parallelism that we exploit in the memory system. We want to optimize for locality and so on. So the memory system, caches, and things like address translation, we're going to dive straight into all of that right at the beginning. Chapter 3 is actually, it's hard to have favorites, but I think it's my favorite part of this course. It's about dynamic scheduling. It's about processors often described as out-of-order processor cores. So back in chapter 1, we'll talk about what I call in-order processor cores, simple pipelined processor architectures. In chapter 3, we're going to look at processor architectures that dynamically reschedule the instructions so they are fetched, decoded, put on a shelf, waiting for the right time for that instruction to be executed. The right time is when its operands are ready and when there's hardware available to execute it. And we'll look at how to do that efficiently. And from that emerges a couple of really big ideas in processor architecture: register renaming and speculative execution. Speculative execution handles the fundamental problem that you fetch a branch instruction and you don't know what the next instruction is going to be. So what do you do? I mean, we talked about pipelining earlier on. Pipelining assumes that you can start work on the next instruction before you've finished the previous one. But if it's a conditional jump, what do you do? Well, what you do is branch prediction, and that's the subject of chapter 4. The way you use it is with speculative execution in chapter 3. Chapter 5, we're going to peel off a little bit and look at something kind of completely different. We're going to look at what you can do in the software to make more effective use of your hardware. And in particular, I want to talk to you about loops and loop nests and loop parallelization, the conditions under which a loop can be executed in parallel. Things like interchanges. So can you optimize the order in which a loop executes, perhaps to improve its temporal or spatial locality, things like that. And I'll show you a little bit of a taste of some of the underlying theory that underpins that work. Chapter 6, we're going to go back to the issue of scheduling instructions. So back in chapter 3, I'm going to argue that dynamic scheduling is a wonderful thing. In chapter 6, I'm going to question that and ask, can we pre-compute what the optimum schedules will actually be and pack that into our encoding of the binary instructions? And so that will lead us to things like instructions or wide instructions or very long instruction words where we actually control multiple functional units in a single instruction. Or you can think of it as explicitly packing perhaps 6 operations into a single instruction so that the hardware doesn't have to decode which instructions can be executed in parallel. The encoding has already, the compiler has figured that out and communicated it in the way the instructions are generated. We'll also talk about how you push that idea to get some of the other advantages of dynamic scheduling. Things like what happens when you have a cache miss. Can you find a way to reorder instructions to account for, or can you move instructions around to hide the access latency of a cache miss? Actually, multithreading is a way of not doing any of those things. And it's going to come up a few times, actually, is if you have more parallelism, then you can do less speculative work. So if you just think about branch prediction for a moment, the idea with branch prediction is that you're going to guess whether the branch is going to be taken or not taken and speculate. And then if you're wrong, you have to undo the work that you did. But suppose instead that you can interleave the instruction sequences so that while you're waiting for the branch outcome to be determined, you can be executing other threads. And that multi-threading idea can actually make things much, much simpler. That brings us to architectures like graphics processors. Now, we're not going to talk about graphics processors for graphics rendering. We're going to be talking about graphics processors for computing. And what I'm going to try to do is to explain to you how a graphics processor fits into a spectrum of architectural ideas that includes ordinary processors too. We'll see how graphics processors, GPUs, are essentially, simply, mostly a variation on architectural ideas that we're already familiar with. The key one is data parallelism, the idea that instead of operating on individual elements of a data structure, for example an array, at each iteration of the loop, we might bite off a chunk, perhaps 4 or 8 or 32 operands with each instruction. And of course that leads to all sorts of tricky questions like, can we line up all the data? What happens if the loop contains if-then-else's, and so on. Chapter 8 is where we look at shared memory multiprocessors and large-scale parallel computers. So one of the things I want to show you is how to build a multi-core machine where every core can see a consistent view of a shared memory, despite the fact that every core has its own cache. That's the cache coherency problem. I'll also talk about how you make that idea work for larger computers. And many people will tell you that it kind of doesn't work for larger computers. That, I think, is something to reflect upon rather carefully. But there are alternatives to shared memory. We could use message passing. We can write parallel programs that work by exchanging messages between processes, all collectively operating, executing perhaps iterations of the same parallel loop, but distributed across a number of processes, each with their own separate memory. And we will try to get some insight into the price to pay for that distributed memory strategy, the potential advantage of a shared memory approach, and the issues in designing a cache coherency protocol and an interconnection network for your computer that might make that idea work. And there's room for argument on both sides there, and I hope that by the end of the course you will be equipped to make those arguments yourself and tell me what you think. I mentioned there's a couple of coursework exercises, and I've already said something about the exam, and again I strongly encourage you to look at the past papers. So just to wrap up, firstly, a little bit of administrative detail. If you're a student from outside the Department of Computing, then it's absolutely essential that you get registered formally for this course as soon as possible. This will enable you to participate in the online forums that we'll be using, and it will also enable you to access the computers necessary for doing the unassessed and then soon also assessed coursework exercises. So it's absolutely crucial. So to conclude, if you studied computer architecture before, then you should be able to do this course. If you've never done computer architecture before, then probably this course isn't for you. But if you know what a pipeline stall is, if you know what a cache miss is, then you're probably in good shape, I think. You will need to do some work if these ideas are not completely confident, if you're not completely confident with these ideas. You will need to do some C programming on Linux. You'll need some Linux command line and bash scripting and so on. If you're uncomfortable with those things, then you might also think about whether this is the right course for you. But for computing students, certainly, and I think for most electrical engineering students, that should be just fine. By the end of this course, you should understand the main features and design alternatives in computers used today. We'll look at a spectrum of scales from the microarchitecture of single processor cores for low power, so simplified, highly efficient architectures, all the way up to the highest possible performance in a single core. And then we will look at multi-core systems, how to connect your cores, what kind of memory consistency properties can be maintained, and what you need to do to get that, so the cache coherency protocols. We'll talk about graphics processors, as I mentioned. There's another kind of multi-core, sometimes called a many-core processor. We'll talk about large-scale systems, including supercomputers. The course's examinable content is defined essentially by the lecture slides, rather than the textbook. It's the lecture slides are what you need to be reading, but you need to be reading a bit more beyond that, I think, to kind of fill in some of the gaps and to get a bit more kind of confidence with the ideas. So my aim as a lecturer is to be your guide into this field. The textbook is a good place to get some of that depth, but actually there's an enormous amount of good material also on the internet. If I say something confusing, you don't follow my slides, check the slides of other people teaching courses a bit like this. You may find them to be quite similar. You may find that they give you a bit more understanding. And I mentioned there are a couple of coursework exercises, and you do need to have a look at how the course is going to be examined. My objective, of course, is to support you in being a successful student. I get no brownie points for failing students, but what gets me out of the bed in the morning is when you learn exciting, interesting things. With that, thank you very much. I hope very much that you choose my course. The next pure chapter is going to be on elementary pipeline processor architecture. We'll go swiftly into caches and memory and so on. Along the way, we'll have some discussion exercises. We'll kick off with one on what I call the Turing tax. I hope you enjoy it. Thank you very much indeed.